Hey there, School of Tomorrow students. So, you know what we do here? We kind of, it's kind of a one-way street because I'm making the YouTube, so I'm like coaching you, but in the real world, we're all coaching each other, and this is just one sort of compression rod of me pushing out, content. But, I consult what other people are doing, and I spend a lot of time learning from you, so it's not a one-way street, really. For example, I learned a lot from Trevor Blake, who features in this recent documentary about the Church of the Subgenius. He's taught me about that originally when it first showed up, and when I first showed up in Portland, actually. I can't remember which of us was already living in Portland. I came back to Portland in '85, having gone to university on the East Coast and worked on the East Coast, had some startup careers. So I came back in my young adulthood. I was already, let's see, um, well, I wasn't married yet, and I got married and raised my family here in Portland. Anyway, then I met Trevor and I learned about Church of the Subgenius, and he's very involved in the Bucky stuff, as I call it. Synchronophile, you may recall, I featured in a recent video because it had been hacked, as had been my grunch.net. There was a spate of failures of websites that were all relating, well, not all relating to Bucky, actually. I don't know, I'm not imputing a conspiracy, actually. But anyway, a bunch of websites succumbed at the same time to malware of different, who knows of what origin. WordPress isn't that hard to mess with, right? So what I'm going to do this time is go to some choice slides and support you guys who are trying to figure out if you want to use my slides or already are. And by slides, I mean a specific slideshow I've done a few times here. I should put this in full screen mode, perhaps. I don't think it matters, actually. So that's where we're going to start in a second. But I also wanted to, as background, say uh, I haven't kept up with all the readings yet in Transcendentalists, but I'm very happy to see the the seamless integration of, say, here's Emily Dickinson right next to Margaret Fuller, and some conversation going on about all these transcendentalists, because as you know, I'm treating the Bucky corpus more as a literature inside of American transcendentalism than I am a STEM topic like Springer Verlag would deal with, right? But then there's a bridge across the CP Snow chasm. It's just we sort of study on this side of the bridge. And when I say this side, I kind of want you to know what I mean. That it's not really STEM, right? Not when we start out. So going forward on this, I'm suggesting you get over the dome real quick in this particular slideshow, not in all of them. In other words, if you're a Joe Clinton or somebody who knows domes inside out, you may have our spiel just on domes and dome architecture, dome history. Who were the engineers, right? T.C. Howard, all the people. But what I use this slide for is sort of introduce myself, perhaps, and then make domes not be the topic, even though we're talking about Buckminster Fuller. I'll probably introduce mnemonics, in other words, helping you remember stuff. That's really important and valuable to have organized knowledge rather than a hodgepodge that you have to put together. Someone just throws a jigsaw puzzle at you. That's a whole different thing than you're handed a completed jigsaw puzzle. Now, of course, if your fun is putting together pieces, you could say, well, you took the fun out of it. You gave me an assembled puzzle. But really, there's so much to assemble anyway. We treasure well assembled puzzles. So that's what I'm trying to get across here. And so I want the dome to stay a puzzle piece because that's how people have remembered Buckminster Fuller as an architect, engineer kind of guy who was deeply involved with the domes. And if you go to this one in St. Louis, you'll see a plaque, and his name will be on it. It's not the only one on it because it was kind of a movement. And part of what I want to cover as we switch away from the dome and go more into his synergetics is that there was a movement involved in all of this. In other words, what we're tracking here isn't necessarily just one person's dream, it's a collective dream that people are going in parallel and crisscrossing a lot, right? Seeing in each other's work reflections of their own. And this is especially true with sphere packing, right? In the 1900s, sphere packing is a huge topic, multidimensional sphere packing. And it was for Fuller too, and you see on the right side that we end with the little brown sphere there, but in between we've got a sort of a rotating cast of, by rotating means cycling through, talking about the animated GIF on the right. This is the kind of thing I do early in Python. Not that Python is especially good at doing graphics on its own, but as a glue language between sort of math concepts and ray traceable stuff, it's great. So, but it doesn't have to be Python. I started out using FoxPro, doing the exact same thing because that was my career language at the time. So this slide, see, this is where to kick things off for synergetics, because something's got to give in our normal thought. Because looking at this cube and telling the audience that that tetrahedron is our unit of volume, right? We're going to call that 1. That can't be if we don't break something, because why? The cube, by definition, say it has edges second root of 2. The third power of that, and precisely what the cube of that would be, is represented by this shape, like this sugar cube here, with edges second root of 2. And a third of that, you can prove, it's like a well-known fact of geometry that, maybe not that well-known, but any parallelepipede, in other words, it doesn't even have to have right angles, but it's a hexahedron of this kind. Let's say a cube is the simplest version. If you inscribe a tetrahedron inside of it using its face diagonals, as we've done here, and there's a couple ways to do it, you get the same volume each time, and it's always a third of the cubes. And if the volume to start with is second root of 2 to the third power, 1/3 of that cannot be a pretty whole number. Let's just put it that way. Second root of 2 to the third power, 1/3 of that, that's not, it's an irrational number. Let's get over that. But see, in synergetics, we want to have our cake and eat it, you could say. No, we want the volume to just be 1, and therefore the cube has to have a volume of 3. Well, how can this cube have a volume of 3 if the edges are second root of 2? And that sets up your tension. And your ability to talk your audience through that tension and show them the way to the other side of that sort of gestalt switch. That's your job as the presenter, is to lead them by the hand to where the tetrahedron could actually be the unit of volume and still have a unit edge, or we can also call it 2, because of what? Diameter radius relationship. You can call it 2R or 1D. Either way, that's our prime edge. But then the way we do volume is different, and there's going to be a 2D representation as well, like a flat version of what we do. So Fuller is, why I call it philosophy of math in a way, is because he's digging down to our, well-established meanings, where three-dimensional means what it means. We all know what it means. We're taught since grade school about 1, 2, 3 dimensions. And Fuller is daring to be contrarian at that level. And people in high math, they shouldn't have a problem with that, because what you realize as you sort of pass out at the top of math, as you become versatile and fluent in math, is you realize that math has room for these different namespaces, right? The way we use the word dimension, it's fixed and disciplined and tight inside one or another structures, and these structures are more or less free floating from one another. In other words, we we like the meaning three-dimensional that we learned from schools because it helps actually with what we mean by 4D. It's like they go together. But once we have a unit volume 4D tetrahedron, we find how it divides evenly into these other primitive shapes, and we're really not trying to do a full inventory of all polyhedron. I mean, we can, and there's a lot of fun that we can do. What we do in this curriculum actually is bite off way more than anyone could chew in a suggestive way, the way we go with the trailheads, where you see topics that, for all I know, for all you know, no one has explored this trail. No one, right? Like what what tetrahedra fill space? How many people just spontaneously ran to that problem throughout world history? Because way back to Aristotle, they say he made a mistake, right? It's like part of chipping away at his authority, because too many people were just like, oh, whatever Aristotle said. Might is Fuller's invention. Minimum tetrahedron is not that stupid an invention, and it is for a space-filling irregular tetrahedron, and there are such. And no, they don't have to have handedness. So what are the ones that don't have handedness? And is this the only one? We see right away it can't be the only one because it makes two of them make something that's also a tetrahedron. 1, 2, 3, 4. That's also a space filler. So it gets to be where we need to classify. And there's a mathematician named Somerville. Check it out. Did he and Fuller ever correspond? I have no idea. I doubt it, right? In other words, back to my earlier point, this dream was in the zeitgeist. There was a lot of people thinking about sphere packing, thinking about space filling, because history moves on, right? We're done with the 1800s, we're in the 1900s, and Fuller's cresting along with the rest of us in his sort of dream time, traveling around the world, trying to solve shelter problems, and dreaming of this kind of philosophy in the quiet times. And then he's going to distill it towards the end of his life into something that's actually publishable with help from his friend E.J. Applewhite, who I know in this story, right? He's somebody I know spent more time with than with Bucky, right? A lot more. So T&E modules. So this is going to be very interesting tautology stuff. In other words, it's not empirical in the sense that once you start with these definitions and work forward and want to find what has volume 5, you have this very intriguing discovery that a rhombic trichontahedron shrink wrapping, we could say, it centers at the exact radial tips of a sphere, the unit sphere. Its tetravolume now is a little more than 5, but how much more? Not much more. And we get into the math of how much more. So we're interested, you could say, in this concentric, you could call it, I don't know if you want to call it a spectrum, but you could, because, we want spectra now to be seen. We want the idea of frequency to be from inside out to like lower frequency with really high frequency in the middle kind of thing. Like the rainbow isn't good enough in some cases. You'd rather have a sphere for your spectrum. But forget spectrum. Before we even get into a spectrum, you just want to have like Russian dolls of shapes nested kind of together, kind of like Kepler was doing, except we're not saying, oh, this is the solar system or this is something out there in the world. No, it's its own strange attractor, the so-called concentric hierarchy, in its own right, is worth studying as a pure math thing with our new lens of tetravolumes. So getting into the E and the T modules, how they relate, that's a big part of A, Synergetics, and B, this slideshow, because now we are in the core nomenclature of what is unit volume, how does this language distinguish itself from the neighbors, right? And Synergetics should be thought of as like kind of a squishy sponge that you can put in wherever you've got multiple languages that you might find some common ground in Synergetics. In other words, like Python, I'd say it's kind of a glue language, and that Fuller was showing us, as he was around to do so, how explorations in the geometry of thinking might look. And it's an experiment, right? And then writing it in prose and making it literary, that was an experiment and a bold one. And so now the question is, what do you write when you think synergetics? In other words, you don't want to be a parrot of Bucky, right? So what synergetics look like coming from others? How is it continuing in the wind? In other words, the zeitgeist rolls on. And one way is through Gerald Zhang, who's really into tensegrity as I'm talking now. He's very active with his project Pretense and so forth. Lots of computer modeling going there. And this is from the old days, you could say. And it may not even be my most favorite expression of it. And I've done it in other languages like Clojure and Rust or whatever. Because it's just your archetypal algorithm. And you can find these algorithms for the Tetrahedron quite a long time ago. Like in the Italian Renaissance, there was one. But it looks similar to this. It gave back the cube volume. Excuse me. Where's my coffee? Here. Yeah, the cube volume. And it has a big constant in it or something. I'll get a picture of it. So this is very streamlined, and it gives back the tetra volume natively. But then we have a conversion constant. And the conversion constant is showing on the right there. It's 1.06066, etc. And this is going between like two currencies, like American dollars and Canadian dollars, or US dollars. And so you've got a lot of low-hanging fruit. And David Koski, I get into his work around here, has done all kinds of interesting work with identities involving phi scaling some of these modules, especially the S and the E. If you scale them up and down by phi, and then use those as your units of not your units of volume, your sort of components of volume, you can get whole number coefficient equations for, our volume on the left, like the cube octahedron, equals so many. Let's see, do I have these written down nicely in just one place here? I'll have to pull up a couple other slides too, or a couple other Jupyter notebooks to make it more clear what we're talking about in terms of identities. But you've got all this math going on, and it's going on in so productive a way that it can't be contained by its literary context. And so it sort of leaks out, it vents, it releases pressure by storming over the CP Snow Chasm Bridge and coming into STEM through, you could say, the topic of sphere packing and structural integrity and tensegrity, and just these two contrasting ways of carving up space. Whether you do it with cubes, or whether you do it with XYZ coordinate system, or whether you're in some kind of alternative, a different, more exotic kind of geometry, but that somehow seems more natural because of the 60, 120 degree kind of way it's the right angles that we have from architecture and from years of doing rectilinear stuff. That architecture is a bit alien compared to nature itself. In other words, we're a bit anomalous in how right angle focused we are. And again, Adventures in the Zeitgeist, bigger than Bucky. This is like he came to this insight and expressed it. He like distilled into words what I think was happening kind of in the collective dream, which was through carbon chemistry and hexamers, pentamers, through the eyes of the organic chemist, we were seeing hexagons everywhere, which aren't squares, right? And we're seeing that molecules and so forth are much more in this non-rectilinear pattern. And Fuller is always sort of being pulled into biology by virologists, by later carbon chemistry. It's like, hey, the stuff you're doing with the domes looks like nature does stuff like that too. And that's why Buckminster Fullerene was such an apt name, right? Anyway, the quadray coordinates, I go through this in great detail on this channel. For those of you who don't want to go through them in great detail, this telling is for you. Just say, here's another trailhead, you know? Go down quadrate coordinate trailhead if you feel like it. There's a lot of material online. It really will help your understanding of, first of all, what Fuller means by four-dimensional, but also just reinforce all our volumes, and the way it's done in Python is going to help you with Python and so on. So it's a trailhead. But here's the core of it. Here's the core of it. And this is where we go back to math has room for multiple namespaces. It's not a problem. We've already got, at the end of the 1900s, a bifurcation between 4D as meant by Einstein, which has time as the fourth dimension, and then three spatial dimensions, height, width, and breadth. Height, width, and breadth. 3 plus 1 equals 4. That's Einstein. And relativity and blah, blah, right? But then there's a kind of extended Euclidean geometry where all your axes are equally spatial. Time isn't really introduced algebraically. In fact, time has kind of fallen from the Platonic forms. You don't need time in it. Everything's made out of ice. I don't know. There is dynamism. Let's not be over the top about it. But anyway, the Euclidean tradition doesn't bow to time, and yet it still adds many more axes, as many as it wants, has n dimensions. And n-dimensional polytopes are not really the same kind of like manifold that you would find in a relativity treatise, right? The black hole and so on is not really 4D in the same sense as a machine learning model that has four parameters, right? That would be more like a geometric space. And this whole machine learning revolution that's going on is kind of in the second meaning of 4D. So the Einstein meaning, the extended Euclidean or second meaning is the Coxeter meaning, H.S.M. Coxeter. He's the one we're dedicating Synergetics to in the first place. His meaning and the Einstein meaning are the big 4Ds before Bucky comes out with Synergetics and tries to like kind of dig his grave next to theirs with his 4D. Like he wants to be remembered for 4D too. He's had a logo going all his life with 4D, and he's got a meaning for it. And it's related. It's in the right ballpark. In other words, I don't think it's a big stretch to include a third 3D, to include a third 4D, got it, in our sort of summary of the 1900s, because Fuller squeaks in there at the end, in the late 70s, with this synergetic stuff. So we kind of go into the 1900s excited about fourth dimension, not sure what it means. There's a huge amount of ferment. By the end of the 1900s, it's kind of shaken out for most people into the first two, right? Relativity and polytopes. And then for a subculture, my subculture, there was yet a third 4D that was kind of under the radar for everyone else. And it relates to the tetrahedron. And here we are doing, now I'm going to mix the namespaces. Here's the 2D version. Now we all know that 2D, right? So here's the 2D flat version of what we call multiplication. And this is where I would go to Utragon talk at the Canberra website by that Principles of Nature guy, because he discovers this on his own and proves it, and he's very excited about it. And then we add a dimension, so you could say three-dimensional, but the way we do it in Synergetics is once we're in volume or space, we don't really accept that we have to go lower and accept anything below sort of res extensa, right? It's volume and that's it. And then there's pure nothing, you could say. I don't know. Like, let's just say we want to be very definite about our limit. And when we look at a point, we're already not the point. So if you imagine a point in space, you're already just different from that point. So there's already volume just in imagining a point. It's kind of like when you imagine the Big Bang. Who are you? There's a lot of forgetting the subject. The point of view doesn't matter. And we have to, that's not good. We have to educate ourselves out of that oversight, where we pretend that the observer doesn't have a specific viewpoint. It's God's eye view. Well, no, you're actually looking from a specific viewpoint. Get over it, right? So we have to bring the subject back in some ways to understand the nature of space, what it is, right? So we have many opportunities to weave in philosophical threads like that. And I'm always going forward in the slides here, but I'm coming back to the original topic. And I'm hoping by now at least half the audience at least sees that it's possible to have both. In other words, you can continue with the math you've always had and always learned. And oh, there's another way to do multiplication, A times B times C, where you're picturing not the edges of a cube, but the edges of a tetrahedron, all coming off the same point, a regular tetrahedron, right? And you just close the lid. That's your operation. With 2 or 3 dimensions, you just connect the tips of the 2 vectors or 3 vectors in question with either a slanty line or a slanty triangle. And that closes the lid, and you've got your volume, and it's just a different cartoon. And then we get into, again, the Zeitgeist. Darcy Thompson, he's thinking 4D, and he's thinking this at the beginning of the 1900s. So when the shakeout's just starting, and Carl Menger and his essay on a geometry of lumps. And he's a very well respected, established Vienna Circle kind of mathematician who knows his way around. And he's just saying, implicitly, Euclid maybe never uses our talk, or maybe he only implicitly uses our concept of dimension the way we do. Like the points have no dimension, lines have 1 dimension, squares have 2 dimensions, and cubes have 3 dimensions. That's what we learn in school. Now, I don't think Euclid had a strict use of the word dimension. Like, what would it be in Greek, dimension? And where can you find a passage where he spells it out quite like that? But whether he does or not, here in the Einstein period, we're starting to see that we can vary these axioms. We have that freedom. And if we don't want points to be 0, if we don't want points, lines, planes, and cubes to be respectively 0, 1, 2, 3 dimensional, maybe we don't have to. We can make them all take up volume. It's just topologically, flat things are more like pancakes, and points are more like round things, or maybe tetrahedra even. In fact, you can start with a tetrahedron as a home shape. Why not? Pick one. And you can roll it out into a long spaghetti. There's your line. Or you can roll it into a ball. There's your point. Or you can roll it out flat like a pancake. There's your plane. As big as you want, whatever. It's all relative. So this is the kind of thinking that Fuller is playing with, but it's already in the zeitgeist. And he's just going to roll it all up into a nice, accessible for what it tackles. Synergetics is remarkably readable, right? Because it's about all this Platonic mathy kind of stuff, but it's in ordinary, you could say, ordinary language. Now you could also say extraordinary language, because he uses the words in extraordinary ways, and that's what makes it philosophy. But nevertheless, it's not all done in sort of a cryptic, it's not all differential equations and like that. And yet there is discussion of precession and angular momentum and, is there such a thing as equal and opposite? It even questions the equal and opposite, right? It's like it's an alternative sort of look at the world, but not an insane or crazy one, actually. And that's where we get to the quixotic part. I'm saying, no, this is establishment reading now. It's like in the better schools, we all know this stuff already. And we're just slowing it down for the rest of you, okay? So give your audience a sense that they're not wasting their time. Encourage them to look into the whole history of art and non-Euclidean geometry per the book by Linda Dalrymple Henderson here. It's called The Fourth Dimension and Non-Euclidean Geometry in Modern Art. And this is the most recent cover. And there's Fuller's 4D next to it. And this is an emblematic page because it puts it in context that we had a whole century and a whole movement around the concept of 4D, and it's not done, right? There's still multiple prongs, like when you go to Git and there are many forks. That's not a tragedy, and the goal is not to unify everything. It's not one namespace, uber alles. It's not when do we finally converge to one namespace. It's not even a goal. Okay, I hope that was helpful. Enjoy using these slides, and you don't have to let me know when you take them on the road. I'll find out later maybe or maybe not. But give me a shout out and a link if you want me to take a look, and we'll talk again. Hang in there, folks.